Hi guys, in this occasion we are going to solve a problem about uniform circular motion in a vertical cycle. Okay, the problem says a passenger on a Carnival Ferris wheel moves in a vertical cycle of radius r with constant speed v. The seat remains upright during the motion. Find expressions for the force the seat exerts on the passenger at the top and at the bottom of the cycle. Okay, uh, the forces we want to find are the normal forces. The outward normal force the seat applies to the passenger at the top of the cycle, and the normal force at the bottom. So we will find these forces using Newton's second law and the uniform circular motion equations. Okay, here in this figure we can see that the passenger at the top is moving to the right. Okay, at the bottom the passenger is moving to the left, just at the point. Okay, so we have the velocity at the bottom pointing to the right, and the velocity at the bottom pointing to the left. The passenger's velocity and acceleration at the two positions are showed at this figure. Okay, what is the acceleration at the bottom? At the top, the acceleration, the radial acceleration, is pointing downwards, and by definition is v squared dividing the radius. Alright, in the same way, the acceleration or the radial acceleration at the bottom is pointing outwards, and by definition is v squared dividing the radius. Alright, so at each point the only forces acting are vertical: the outward normal force and the downward force of the gravity. How does it work? Okay, let's go and write the free body diagrams at the 2 points. So this is the free body diagram. Diagrams at the bottom or at the top. In this case, we are going to write the free body diagram for the passenger at the top. In this case, the passenger is moving just at this point, is moving to the right, and he is here. This is the y-axis. This is the x-axis. Okay, in this case the acceleration is pointing downwards because he is at the top, and if you remember, at any point the acceleration is pointing to the center of the cycle. It doesn't matter where the point is. For example, if I am right here at this, or if the little passenger is right here at this blue spot, the acceleration at this time is pointing to the center. But if the passenger is on this other position, the acceleration is pointing at this occasion to the center. Okay, whenever the passenger is, or wherever the passenger is, whatever point the passenger is in the cycle, the acceleration is always going to point to the center of the cycle. So because we are writing the free body diagram on top, on this case, so the acceleration is going to point downwards in this case. So the acceleration is going to point downwards. Okay, this is the acceleration pointing downwards. And what is this force? This force is the weight of the passenger, as is equal to his mass multiplying the gravity. Okay, and this normal force is the reaction of the seat on the passenger and is pointing outwards and is equal to nt. Okay, so that's the free body diagram on top. Okay, so now the free body diagram on the bottom is, in this case on top, and this case at the bottom. Basically we draw the same situation. Basically, here is the little passenger right here at this point. The coordinate the system of coordinates is this. This is the y-axis. This is the x-axis. We know that the weight is always pointing downwards to the center of the earth. So this is the weight. W is equal to the mass multiplying the gravity. The normal force in this case is NB, normal force, or at the bottom, and this is a normal force NT at the top. Okay, T means top and B means bottom. In what direction is the acceleration pointing in this case? Okay, because he is here, right here at the bottom, so the acceleration is pointing outwards in this case. The acceleration is pointing outwards. Alright, we remember that the acceleration or radial acceleration for a circular motion is equal to radial acceleration is equal to v squared dividing the radio. Okay, by definition, this is the radial acceleration of an object that is moving in a circular motion. All right, so we are gonna use first the equation on 2 or the second Newton's law to find the normal force at top of the cycle. Alright, so we are gonna use this free body diagram, this first one. Okay, we use the second Newton's law. The second Newton's law, you remember that the total force acting on a body is equal to its mass multiplying the acceleration that this object has, or the acceleration that this object is moving with. Applying the second Newton's law to the little passenger at the bottom of the cycle, we have total forces on the y direction are equal to, okay, what forces are pointing outwards? In this case, the normal force at the bottom, at the top is pointing outwards, so the force is going to be positive. Normal force at the top. What is the other force acting on the passenger? Okay, the weight, and it is acting downwards, so it's going to be negative. These are all the forces we have in this case, by definition, that is equal to the mass of the passenger multiplying the acceleration. But in what direction is the acceleration is pointing? The acceleration is pointing downwards in this case, so the acceleration is going to be negative. And if we remember that the radial acceleration is equal to the magnitude is v squared dividing the radio, but the component at this point is negative, so in this case it's gonna be negative because its direction is downwards. That way this equation is gonna be like nt minus mg equal minus v minus m v squared dividing the radio. Alright, so what we do now is this: we take this mg that is subtracting on this side of the equation, this mg that is subtracting on this side of the equation, and we are going to move it to this other side of the equation with different sign, with positive sign, right? It's subtracting here, so if we move it to this side of the equation, it has to be adding. Alright, so we have nt equal to minus m b squared dividing r plus mg, and we take this m as common factor out, and the equation takes this for mt is equal to m multiplying minus b squared dividing r plus the gravity, and this is the normal force at the bottom. Okay, at the bottom. We can highlight it. Sorry, we can highlight it like this. And we can call this equation number 1. Okay, the second part is to calculate the normal force, but at the bottom, in this situation. We calculated the normal force at the top already, but now we can calculate it at the bottom. And what we do here is this. We remember that the acceleration is pointing outwards. Okay, the acceleration is pointing outwards. Because the acceleration is pointing outwards, the radial acceleration equal to v squared dividing the radio is going to be positive because it is pointing that outwards. Remember that the previous case, because the acceleration was pointing downwards, we had to put it like negative, but now it's pointing outwards, so it's going to be positive. The process is the same. The procedure is, the calculation is the same. Using the second Newton's law, we know that total force pointing in the y along the y-axis is equal to the mass multiplying the acceleration. But the total force is equal to what forces are acting along the y-axis. Okay, the normal force at the bottom and the weight. The normal force is pointing outwards, so it's going to be positive, minus the weight that is pointing downwards. It was going to be negative. That's equal to the mass multiplying the radial acceleration. But we know that the radial acceleration in this case, what is? Okay, it is v squared dividing the radio, and it's positive because it's pointing upward. Okay, that way the equation is going to take this form: mv minus mg is equal to the mass multiplying the v squared dividing r. And because this term is subtracting on this side of the equation, we are going to move it to the other side. But because it's subtracting, it's going to be adding on the other side. And it's going to take this form: mb is equal to m multiplying v squared dividing r plus mg. And if we take common factor m and we take the common factor out, we are going to take m multiplying v squared dividing the radio plus the gravity, and that normal force is m v squared dividing the radio plus the gravity. Okay, this is the normal force that the seat exerts on the passenger at the bottom of the cycle. Okay, if we compare this equation, let's call this equation number 2. If we compare this equation number 2 with equation number 1, what we are going to do is this. I'm gonna write equation number 1 here, right here. Mt is equal to the mass multiplying. I'm gonna change the order. The order is minus b squared dividing r plus g, but I'm gonna write here is the same. G minus b squared dividing r. This is nt. Okay, it's the same, just I change the order of these terms into the parentheses. This is equation 1, and equation 2 I'm gonna change the order to. It's gonna be m g plus v squared dividing r. So this is equation 1 and this is equation 2. Okay, can you know something? Can you see that the force at the bottom is different from the force at the top? What is the difference? Okay, this result is telling us that at the top, the force that the seat applies on the passenger is smaller than the force at the bottom. Okay, so why does this happen? Why? Okay, this happens because the acceleration is different. It happens because the acceleration at the top is pointing downwards, and at the bottom is pointing upwards. So this is the problem that we wanted to see in this occasion, and hopefully it helps you to understand some physics. See you in the next video. Bye.